All right, here we go. Lesson 4.4, distances and angles. Specifically, we're looking at angles which are equal and distances that are equal. All right. First of all, the shortest path is defined as a distance, and typically we call that a line segment. So we have a postulate that says a line segment is the shortest path. You don't ever need to quote this particular postulate, okay? And I'd better write shortest, right? All right. So if I look at A and I say, how far is A from B? That would be the distance from A to B. And that would be the distance from A to C. And we are going to use a phrase called the equidistant. And that would then imply that those two distances there are the same. Okay? So here is a formal definition of that. If MI, that distance is equal to NI, that means I is, fancy word, equidistant from both M and N. All right? There are some diagrams that you've already seen which have used that concept, and you didn't necessarily know that. So notice the red point would be equidistant from M and N. In the next diagram, we have two red points that are equidistant from M and N. And likewise here we have 2 points equidistant, right? Notice if this is A and that's B, right? A is not the same distance from M as B is to M, but A is equal distance from M and N and B is equal distance from M and N. All right. Next, we put those concepts together with an angle concept, and we have a perpendicular bisector, okay, of a segment is both, oddly enough, perpendicular and a bisector. So here's a little diagram. PQ, right? Perpendicular, and it cuts AZ in half. So PQ is the perpendicular bisector of A to Z, so AZ. All right? Theorem, two theorems here. If 2 points are equal distance from 2 points, then the first two make a perpendicular bisector of the second ones. So again, if we make a little drawing and we say, for example, okay, here's A, well, let's go M and N. All right, and we say M is equal distance from I and A, Iowa, right? All right, so this distance here is the same as that distance there. And that distance there is the same as that distance there. Then we know that the first two, so let's draw a line between the first two, that make a perpendicular bisector of the second two. Okay, so the red one cuts this one in half. Be careful, the red one is not, MN is not cut in half, right? All right. So M and N are equal distant. And I should have marked that equal distance. Okay. Then finally, if you are on a perpendicular bisector, yes, then you are equal distance from those points. So let's take 2 points. Again, we'll take California, CA. Yeah. And if you are equal distance, so let's say you're here, right? Or let's say you are here, or here, or here, right? And if you look at those distances between them, so compare that one to that one, right? Compare that one to that one, that one to that one, those distances there. If those distances are all equal, then those blue dots in the middle make up what we would call a perpendicular bisector. So this line is going to cut our given line, AC. It's going to cut it in half, and it's going to be at 90 degrees in that cutting. And here goes a proof. All right, we need to prove that if these two distances are the same, AB and AD are the same, and BC and CD are the same, then BE is congruent to ED. All right, so the red ones have to be true. All right, this is a little bit like a detour proof. Number one, I take that back. It's not a detour proof. AC is a perpendicular bisector. Now, how do I know that this is a perpendicular bisector? Well, that's just because of this last theorem, right? So, this one here, if 2 points are equal distance from 2 points, so notice A and C are both equal distance from B and D, right? Therefore, what is AC? AC is a perpendicular bisector to BD. All right, and that would be the, let's call it the perpendicular bisector theorem, because that's where we end up with, right? So this, the reason for number 2 is the perpendicular bisector theorem. Okay, made that one up on the spot. Pretty good, huh? Number 3. A, C, and E are, they all form a line, right? So they are collinear. How do I know they're collinear? Because remember, we can assume linearity. Fancy word. You can assume that there is a line in that diagram and that AC is there and they're all on the line. You don't have to judge that. E is equidistant. So here I'm going to write equid, right? E is equidistant to B and D. Right? So E has to be equal distance from there. Why? Because E is on this line. So now I'm using this second one. If you're on the perpendicular bisector, then you're equal distance. So this one we will call the Equid theorem. Okay. Finally, if those are equal distances, then we can say, oh, BE is congruent to ED. And that is our definition of distance. Okay. Definition of equidistance. Definition of equid. That the distances are the same. All right? Hopefully those notes help you work your way through section 4.4.